Testing. All right, so the good thing about the exam, listen, there's a lot in this class. The grades are actually pretty decent on the exam for the class overall, but I know that some of you didn't do well, and we'll sort of pick up and we'll move on and we'll continue doing what we're doing. Want to make sure that we're focusing on the book. A lot of those questions come from the book. If you can master the chapters, then you can do pretty well in the exam. But also following along in class and studying your notes. I find that I'm taking classes too, and I find that what really helps me is that I just set aside, I mean, I set aside about 3 hours every day, but for this class, you probably only need to set aside about 20 minutes a day. And if those are focused 20 minutes every single day, then I think it'll go a long ways towards you doing very well in the exams. I think we can all find 20 minutes in a day, right? Find 20 minutes. So set aside 20 minutes. Maybe one day you just read a chapter for 20 minutes or read a small section of the chapter and sort of go over it, make little note cards. On another day, you might go through and work through some old exams. On another day in your 20-minute period, you might go through the notes, all right? So I think the best way to study is to set aside that time every single day. That's true for all of your classes. Like you should be doing that for all of your classes, setting aside time every day. Some classes are going to require an hour or two a day, but I think for this class that you should be able to get by with just 20 minutes a day, reading those chapters, studying the notes, and maybe even working through some old exams. All right? If you want to get together and talk to me about the exam, I'm willing to do that. I don't usually go over the exams in class. The exam is this class is not cumulative. Like everything that we study is important, and because you guys will see a lot of this later, but we don't have any cumulative exams. So if you didn't get these first couple chapters, you know what? That's not a huge deal, except for the exam if you didn't do well on it, because we're not going to use much of it as we move along. We'll see new material as we move along. Okay? I also want to encourage you too that there's a lot left in this class. We have all the quizzes and the class participation. That counts for quite a bit in the class, as well as the project at the end of the semester, which I'll tell you more about later. That project counts for 150 points, which is a lot for this class because I understand that some of you are really good at taking exams. I'm not one of those people, and then some of you are like me that you're not very good at taking exams. So I've had students that have done poorly on the exams, but they still come out of the class with a B or an A. That certainly is possible. You feel encouraged? Do you? Wow, I'm really like that was my goal, is to make you feel encouraged. That even if you did poorly on this exam, that it's not all lost. In fact, not by any means is it all lost. Okay? 20 minutes a day. That's what you need to be doing. Like I said, in all your classes. And if you're finding that you're not doing well in your other classes, that's really the tack to take. Maybe an hour a day if it's a higher level class, but I think for this class, 20 minutes a day should suffice. All right. Any news since we last met? No news. We had an exam, but that's not really a meeting. We don't really get to talk. No. Let's see. I'm a coach for a math team. Did y'all know this? Do you know that I was a coach? Like not in the way that some of you might be coaches, or at least work with coaches, but like a math coach. They still call me coach, but I don't make them run laps or anything. I make them do fractions. But it's a middle school math team, and I tell you, we went to competition this past weekend. And what place do you think we got? Second. First place. Yo, man, we not only get first place, but we destroyed them. We killed everybody that was there. All those little kids, sixth, seventh, and eighth graders, we destroyed them. We pummeled them. They were crying in their boots. So we're going to state. It won't affect y'all because it's on a Friday, but you'll probably hear about it. And not only that, did we get first place, but we had the first individual. And then one of our sixth graders, this young lady who's awesome, she got sixth place overall. She beat out all these eighth graders. Like it's mostly just eighth graders there, and she got sixth place overall. Isn't that cool? And you know what? She's not like your typical I'm a sixth grade dork and I like math kind of young lady. That she's really cool. Like she's cool like a lot of y'all. She's a good athlete and but yeah, I was really proud of her. Okay, Something else I want to tell you. Oh, I sent an email out about the Ask the Prof lunch. So as many of you know, I'm a Christian, and my wife and I are both Christian. And sometimes people have questions about that. And so we set aside this time about once a month. So if students want to come and just ask questions, it can be about anything really. Like we'll talk about anything. But we just come together and we have lunch in this little conference room. Just brown bag it or whatever. You can bring in something from the union. We don't provide lunch. We're not that cool. But if you want to come, it's at noon on, I think Friday we said. You're welcome to come. It's usually just a few people, 4 or 5 people, and we'll sit down and just talk. Whatever you want to talk about, whatever questions you might have. Okay? So that's an invitation to you if you wish to do so. All right, we're still on this chapter on fluids. We will see this on the next exam, and there'll be some reference to previous things, but the next exam will be focused on this latter half of the chapter. But like the Poisson equation still comes up, and Boyle's law still comes up, and all those things that we've already covered have come up, but we'll focus, instead of on the physics of it, we'll focus on the biological applications or the human performance applications of these things. So we're going to see the circulatory system, and I think we'll get into the eye, like the pressures in the eye, arteries, and the brain, just different fluids that are in the body. Many of you have probably seen some of this before. Um, so the circulatory system has 2 parts, right? It has the systemic circuit. You need to know what each of these parts are and what they do. And then the pulmonary circuit. Stay where you are. Let me go to the next page for just a second. Yeah, so this one takes blood to the body. Like from the heart, blood leaves the heart and goes out to the body in the systemic circuit. And then the pulmonary circuit, y'all have heard of like what's it, pulmonologist? What is that? What type of doctor is that? Lung doctor, right? So the blood actually goes from the heart to the lungs where it's replenished. So um, this takes the quote used blood to the lungs for replenishment. We don't get into how the lungs work. I don't know exactly how they work, but that would be interesting. Like if you want to do that for your project at the end, that would be an interesting thing. If you know a lot about the lungs from your other class, might be a good idea for your project as we move later into the semester and you begin thinking about your project. Okay, we will consider this system to be closed. We talked about closed systems. That's not a D, that's a CL. We'll consider it to be closed. That means that we have nothing coming in and nothing going out of the system. That's not entirely true with the circulatory system, that you do have exchanges of fluids that are slight. But we'll consider it to be closed, nothing in, nothing out. Remember we talked about this before, how this affects our flow rate. If you recall the flow rate equation at A1V1 equals A2V2, that was based on something being a closed system, so that the volume flow rate at one point is equal to the volume flow rate at another point. Remember we said that if they're different, then that's because either you have extra material coming in or extra material leaving the system. So the flow rate is constant. And just to remind you, a flow rate we call Q, and it is a change in volume over a change in time. So it's measured in units of, cubic meters per second, or maybe cubic centimeters or cc's per second. And then also, since blood is viscous, that means that, it has a certain thickness to it. The Poisson equation applies, and for a viscous flow, sorry, where am I? For a viscous flow, you need a continual drop in pressure. If you recall the Poisson equation, I'll go ahead and write it up here. It'll come back a little bit later. Where was it? It was like oh, there it is. Our Poisson equation was Q equals pi r to the fourth delta P divided by 8 eta L. We talked about what each of these means. This is the radius of your duct or your artery or vein or whatever. This is the viscosity of the blood. This is the length of the pipe or whatever it is you're considering. And then this is our change in pressure. So anytime we have a viscous fluid flowing, we need a certain change in pressure in order to make that fluid flow, like in the circulatory system. All right? You need to know the basic sort of You need to know the basic idea of how blood flows through the system. I think you guys have probably covered this in some of your classes, the circulatory system. Yes, no? All right, you need to know the basic flow. You don't need to know all the little valves and stuff of the heart, but you do need to know the basic system and how it works. So after we leave the heart, the blood flows from the aorta to the arteries, uh, to the arterioles. Each of these are getting smaller each time. And then the last one is what? Capillaries, right. And then as it returns to the heart, after going to the capillaries, it goes through the venules, veins, and then that big vein that goes into the heart, the vena cava. All right, so know this basic order and how these things, come in the order of the circulatory system as I go from blood that's leaving the heart, that's taking oxygen and nutrients to the body, and then as it's returning to the heart to be replenished. You also need to know the four chambers of the heart. Atriums, right? Like if you go into a hotel, the atrium is up high. All right, so where in the heart is the atrium? On the top or the bottom? Top, right. So these two are the left and right atriums. It's not left and right like left and right. It's stage left, stage right, right? So like, was it, which one is this? This one's left, right? It's switched, and this is right. So our atrium and our ventricles. So atrium, I always remember like in a hotel. And so these two are atria. This is our right atrium. This is our left atrium. And then our ventricle. I don't have a good way to remember that. Anybody remember? I guess if you remember atrium, then ventricle is just the other part. Do y'all have a good way to remember ventricle? No, but it's similarly right and left. Just know those four parts of the heart. And then also, blood flows, the sort of the basic flow of blood as it goes through the heart. I have a diagram on the next page to help you if you get confused. And then also in your book, there's a diagram. Blood flows out of the left ventricle through the aorta. It goes through the systemic circuit, goes out and does what it does out in the body. And then it returns depleted to the right atrium. So if you want to, like I said, there's a diagram on the next page, but if you want to think about it, it goes out in this direction, goes out to the body, comes back in to the right atrium. Then in the body or in the heart, it goes to the right ventricle, through the pulmonary artery To the, where does it go? In the pulmonary artery, it goes where? To the lungs, right, to the lungs. And then it returns to the left atrium through the pulmonary vein. All right, that's sort of the extent of what I want you to know about how blood flows through the heart. You don't have to know all the valves and all that business. I want you to know the four major parts of the heart and then how blood gets into and out of the heart. I expect many of you already know the valves, but just make sure that you know the basics of how blood flows in and into and out of the heart. Any questions about that? Again, here's a figure with sort of more details. Know the basic flow. There are four one-way valves in the heart. You can just know that they exist, but you don't need to know their names. Like here's the tricuspid valve. Blood comes in here, and it keeps the blood from going back through. So it sort of opens up and allows blood to flow in, but it doesn't go the opposite way. We'll see that actually with an electrical circuit later, that there are devices that similarly allow electricity to flow in one direction, but not in the opposite direction. Okay, I like to give a figure often, and you have to, I'll take the names off, and you have to label those. So just know the different parts of the heart. You'll see that later. We'll do the same with the eye and other parts. Let's try some of these practice questions. Let's try this one on the left. This is an artery which has plaque built up in it, and so the blood is partially blocked. I want to know now what happens to the speed of the blood flowing through this blocked section. Does it increase, decrease, or stay the same? All right, we'll stop at, say, 42. 42. If y'all do well, never mind. Up to 47. Okay, we're sort of split here. It's like a water hose, right? What happens when you put your finger over the end of the water hose? No, the pressure doesn't increase actually. The s- the speed increases. We'll talk about that. We sort of have this idea that pressure increases, but in fact it's the opposite. But here we're not asking about pressure, we're asking about speed. It's like the continuity equation. Remember the continuity equation said that Q1 is equal to Q2. So if Q1 equals Q2, that's our flow rates. A1 V1 equals A2 V2. And so what's happening here, let's say this is constant, like this is A1, and A2 goes down, right? This is A2. So V2 has to go up. It's like putting your finger over the end of a water hose. And so the pressure here, or excuse me, the speed of the blood is going to increase. Now, let's do the next question and we'll come back to that. So that was the speed increases. A is the right answer. Let's try this one over here on the right. Remember the Poiseuille equation as it relates to the systemic circuit, and it does apply to our systemic circuit. What happens to the overall blood pressure as a blood vessel becomes partially blocked? All right, I'm going to stop at, let's stop at 43, 43. Okay, the blood pressure does increase. We can look at our Poiseuille equation. Remember, Q was pi r to the fourth delta P divided by 8 eta L. is the Poisson equation. It's asking what happens to delta P when R decreases. So if this goes down, I know that it's a closed system, so Q has to remain constant. If R goes down, then delta P goes up. Now that is our sort of our systemic blood pressure, the blood pressure in the entire system, and that sort of makes sense, right? That if you have an artery that is blocked partially, then that can cause an overall higher blood pressure, right? Does that make sort of intuitive sense to you? Sort of as we understand blood pressure? Well, let me tell you that there's an interesting thing that happens in an artery like this. Does anybody know what can happen that if you get so much plaque built up and the blood starts going faster and faster, what can happen to that artery? It gets what? Okay, yeah, that can happen, but it can do what? It's okay, you can guess. No, it's not going to burst, actually. It can do what? It'll collapse. Like the whole thing will just suck down on itself. And in order to collapse, like if I have this artery and it collapses, what does that tell you about the pressures around this artery? Does that mean that I have a high or a low pressure on the inside of the artery? If it collapses down on itself, high or low? Low, right. If it's high, it'll burst, right? But if it's low, it'll collapse down on itself because you have high pressure outside and low pressure inside. So if I have a low pressure here and I have high pressure on the outer side, then it'll push down on itself. This isn't talked about in your book, so I'm not going to test you on it, but it's fairly interesting. It's something called the Bernoulli's principle. You ever heard of that? The Bernoulli's principle? You have, right? You ever been on a plane? That's how planes operate. You have a wing where you have a wing, say on a plane. Don't write this down. This is really just to wow your friends. If you have a wing looks like this. You have air that flows over this side and air that flows over this side. On this side, this is high velocity air, and this is low velocity air. You can sort of think of it as if I have two air particles right here, they have to meet back on this side. Otherwise, you get a vacuum on top of the wing, and that just doesn't work very well. So because this is a longer distance, it's a higher velocity. And what Bernoulli's principle says is that if I get a high velocity in a fluid, I get a low pressure. So that high velocity gives me low pressure and high pressure down here. So that gives you lift. It lifts that huge piece of metal up out of the out up into the sky. And so a similar thing happens here when I have a high velocity of fluid flow in the artery. I get a low pressure, and it can actually cause it to collapse. Now that's a localized pressure. It's not a systemic pressure. The Poisson equation tells me more about the systemic pressure, and that pressure goes up when the radius goes down. But here we're talking about a localized pressure. You follow what I'm saying? Blockages in arteries cause this high blood pressure, but localized, they can have a very low blood pressure. Let me show you a cool little thing. I have these two pieces of paper right here. They're just normal pieces of paper. There's nothing fancy about these pieces of paper. They're not special in any way. But what do you think will happen if I put them together like this and I blow through the pieces of paper? I blow a high velocity stream of fluid through between the two pieces of paper. What do you think is going to happen? They're going to fly apart, right? Right? Think about the pressure. If I blow a high velocity stream of fluid through the middle of the two pieces of paper, it's going to have a low pressure in between them. Now think about what's that going to do. So let's do this. I'm going to blow in between them. They're going to fly apart. Did y'all see that? Did they fly apart? What did they do? They came together. Because when I blow a high velocity stream of fluid through the two, I get a low pressure, and I get high pressures on either side that push them together. Isn't that cool? It's just normal paper. It has your notes on it, but it's normal paper. Nothing fancy about it. So a similar thing happens here. That when I have a high velocity, I have a low pressure. All right. The pulmonary circuit does which of these? Okay, y'all doing really well. I'm going to stop at 33. 33. Remember, you can always ask your neighbor what they put. If you're not sure what the answer is, by all means, ask them what they put. Or if you're sure what the answer is, you tell other people. Don't keep that business to yourself. All right. A is right. Pulmonary circuit takes blood from the heart to the lungs. It gets replenished there, and then it comes back to the heart and distributes to the body through the systemic circuit. I have a joke I want to tell you, but I'm not sure that it's really appropriate. Are y'all okay? Like, I know y'all have tender ears, but is it okay if I tell a slightly inappropriate joke? What did the blanket say when it fell off the bed? Oh, shit. Don't tell anybody I told you that, okay? Don't want to get in trouble. All right, which of these is the rate of blood flow the greatest? Now, remember the sizes of these, right? The aorta is that big one in the heart. Capillaries are the smallest, and the venules are somewhere in between. So which one has the greater, or is the greatest the rate of blood flow? Or is it all the same in the systemic circuit? All right, let's stop at, say, 45, 45. Don't be offended, but y'all are all suckers. Because remember, it's not the size that matters. It's a closed system. So the rate of blood flow is all the same. Watching you, Kai. You want me to write your name on there next to that one? All right. Remember, it's a closed system, so the rate of blood flow is all the same. Now, the speed is certainly different, right? And which of these is this? Well, never mind. That's going to be a little bit different. We'll come to that. But the speeds are different. But the rate of blood flow is the greatest in all of these. All right. So as blood flows through the systemic circuit, it experiences a drop in pressure, a uh, a continual drop in pressure. I'm sorry. Along this path. Remember the Quasi equation, Q, pi r to the fourth, delta P divided by 8 eta L. I have a continual drop in pressure as I move along the systemic circuit. And that's what causes that viscous fluid to flow. I have to have a continual drop in pressure. The highest pressure is where? Where is the highest pressure? In the systemic circuit. Let's go back to our parts of the systemic circuit on the previous page. And then, so this is the systemic circuit going from the aorta all the way back to the vena cava. Where is the highest pressure in the systemic circuit? Miss, you can guess. Where is it? The aorta, right? I have my highest pressure here. And then I have this continual drop in pressure as I go out through the systemic circuit and then back to the heart. So the highest pressure is at the aorta, and then the lowest pressure is where? Vena cava, right. So I have this continual drop in pressure, so I'm continually losing pressure as I go throughout the system. Um, so the highest pressure is in the aorta, and the lowest is in the vena cava. All right, let's see, I have a video I want to show you of the heart. In just a moment, I'll get it up. All right, so Poiseuille's law says that the pressure must be higher for flow through longer systems. It says the pressure must be higher for flow through longer systems. Oh, Poiseuille's law again. So Q is pi r to the fourth. You don't have to write if you don't want to. I just want to show you something over 8 uh, eta eta L. So what that's saying is that if my flow rate is constant, if this is bigger, then I also have to make this bigger. So if I have a longer system and I still want the same flow rate, I have to give a bigger change in pressure. On the other hand, the pulmonary circuit is much shorter than the systemic circuit. Because think about it, right? You're going from your heart to your lungs. It's like 6 inches you gotta go. Whereas with your systemic circuit, you're going from your heart all the way down to your toes, up to your brain, all the way to the tips of your fingers. And so it's a much, much longer circuit. And so the pressure in the pulmonary circuit is quite a bit less. So the pressure there should be less. All right. Just a little bit about different pressures. Let's see, in the systemic circuit, just to give you some idea, in the systemic circuit, our pressure is about 80 to 120 millimeters of mercury. And remember, this is a measurement that's based on a column of height of mercury, sort of a little blast from the past. And if we had a manometer that looked like this, and I have fluid in it, we measure the height. That would be 80 to 120 millimeters of pressure. We've actually measured the pressure of your systemic circuit. And then in your pulmonary circuit, it's going to be about 10 to 25 millimeters of mercury. All right? You don't need to memorize those numbers, but I do want you to know that they're different. That the pressure in the systemic circuit from the heart down to the toes is a lot different. It must be a lot bigger than the pulmonary circuit from, say, the heart to the lungs, just because it's so much shorter. Uh, some of you might go into measurement where you have to measure blood pressure. I expect many of you have done this already, right? You've measured blood pressure of folks, athletes or whatever, patients. All right, so is that a gauge or is that an absolute pressure? It is a gauge pressure. Remember the difference between gauge and absolute pressure? And absolute pressure included what? It included what? It included the atmosphere, right? So the gauge plus the atmosphere. So, but whenever we measure our blood pressure, that's just a gauge pressure. So the blood pressure measurements are a gauge pressure. And if you remember, our absolute is equal to our gauge plus our atmospheric pressure. We have two numbers. I had my blood pressure taken yesterday. It was 120 over 82. Is that good or bad? That's pretty good, right? My heart rate is like 60. Yeah, right. That's good. All right. But sorry, I'm kind of vain about my heart rate because my wife's resting heart rate is like 75, and so I'm always picking at her. It's like, gosh, why is your heart rate so high? But let's see. So 120 is the pressure when the heart contracts. Should be a period there. Systolic. We call this the systolic pressure. Is the pressure when the sorry, is when the heart contracts. And systolic actually means contraction. Notice this is the higher of the two pressures, right? Because when the heart is contracting, I get a higher pressure at that moment. Whereas the diastolic pressure is the pressure when the heart relaxes. I'm sorry, this is a repeat. Diastolic pressure. And diastolic actually means a drawing apart. And that's the lower of the two pressures. You need to know those two pressures. What is systolic and what is diastolic? Systolic means the heart contracts. I have a high pressure, 120 or so. Diastolic means the heart is drawing apart. It's relaxing. That's the lower pressure, of about 80 millimeters of mercury. All right. Let's see. We can think about Pascal's principle is also about Boyle's law. Let's sort of first consider Boyle's law. Remember, Boyle's law says that PV is a constant. This was really for gases, but you can think about it in terms of a fluid here as well. It applies sort of, or at least it turns out to be true, but we can apply it here for fluids. And that's just that if the volume goes down, the pressure goes up, right? So when the heart contracts, that means that the volume is going down, the pressure increases. That means P goes up. And Boyle's law says that the product of these two must always be constant in a closed system. So if the volume goes down when your heart contracts, then the pressure must go up. Yeah, Boyle's law is really for gases, but we can apply it here as well. And then also Pascal's principle. Remember Pascal's principle, the idea behind hydraulic lifts, for example? Pascal's principle says that if you apply an external force or an external pressure to a fluid, then that external pressure is felt all throughout the fluid. And so that's true with the heart as well. Um, the heart applies a pressure at contraction. And that increases the pressure throughout the body. And then when the heart relaxes, the pressure decreases. So that's why we can measure our blood pressure on our arm or on our leg. I mean, it changes slightly depending on where you measure it. But you can measure your blood pressure because when I have a pressure that's applied here, then that pressure is felt all throughout the body. Now, as we know, the pressure decreases because it's a viscous fluid. But nonetheless, if it's higher here, it's higher out here. And that's an application of Pascal's principle. If I apply a pressure to a fluid, an incompressible fluid like water, oil, blood, then that pressure will be felt all throughout the system. That's exciting, right? Pascal's principle. It allows you to measure things like blood pressure. All right, let's try some of these little quick tests. Which of these is greater? Doing the one on the left here. All right, let's stop at 45, 45. We'll go to the right here next. Okay, awesome. The systolic pressure, remember systolic means contraction, diastolic means drawing apart. How do astronomers organize a party? Come on, don't give away my punchline. Huh? They plan it. But in general, you know, in the previous joke, some of you were giving away my punchline. That's just bad etiquette for jokes. You don't give away the punchline. Okay? Mariah, there are others of you, and I'm watching you. All right, let's try this one. According to the flow equation, what happens to the speed as area decreases? All right, let's stop at, say, 38. 38. Okay, we're still having a little trouble on this. So the flow equation, remember, says that Q1 equals Q2. That is that A1 V1 equals A2 V2. Q1 is a volume over time, and area times speed is the same as volume over time because this is meters squared, this is meters per second, so I get cubic meters per second, which is also the unit for Q. So this is speed and this is area. And what this says is that if you have a closed system, that Q remains constant, that this has to be equal to this. And so if I have this as constant and I decrease A, I put my finger over the end of the water hose, then my speed goes up. As I decrease A, the speed increases. So A is right, but I want everybody to be on board with this. So the flow equation. We had it on the previous test, but we can see it again on the next test. Well, let's try this one on the left. Which phenomena caused the distinct sound? We had this, gosh, many days ago. All right, let's stop at 47. 47, just guess if you're not sure. Okay, good. B is right. That's the turbulence. It makes that swooshing sound when you have the drawing apart. And then finally for an IV, should you insert it into a vein or an artery and why? Y'all probably know this, but why is that? Why do you want to insert it into that? So if you're not certain, ask your neighbor if you don't know if you should insert it into a vein or an artery. I think the author wrote about this. Is that right? McCall wrote about this in the book? I'm pretty sure he did. You haven't read this part of the book, have you? That's okay. But hey, let's do a quiz on it next week, next time we meet on the second part of that chapter. How about that? You want to do that? Yeah, that's what I'm talking about. What's today? Thursday, man. Yeah, we should already be done reading that chapter. So, the second part of that chapter on fluids. All right? It's good for y'all, right? We get as many quizzes as we can in so we can drop some of those bad ones. All right, for an IV, should you insert in the vein or the artery? I'm going to take this away in about 5 seconds. 108, let's say. 108. Y'all are some. Who clicked in? Who was that? Wasn't even asking a question. We'll find out. Y'all are some healthcare he-men and women. You know He-Man, Castle of Grayskull, all that business. Good. So why would you want to put it into a vein? Okay. Yeah, but what else? Okay. What? Right. You have lower pressure, and so it's able to go. It's able to move from high pressure to low pressure more easily. What you said is correct, right, Caroline? But I was getting at this low pressure. So the vein has a lower pressure. Remember, we have this continual drop in pressure as I move from the aorta all the way throughout the systemic circuit, all the way back to the vena cava. I have this continual drop in pressure that's predicted by the Poiseuille's equation. What happens to the blood, the speed of the blood, as it moves from the aorta to the capillaries? Does it increase, decrease, or stay the same? Let's do this as a clicker question. We'll do A, B, or C. Increase, decrease, or stay the same? And I just drew a little sketch. I didn't draw this. I got it off the internet. The artery, here's the capillary, the vein. What happens as blood flows from here to here? Because notice the capillaries, they're tiny compared to the aorta. I think you can like stick your finger in the aorta, and the capillaries, smaller than millimeters across, a millimeter or less across. What happens then to the speed of the blood as I move from here to here? What happens to the speed of the blood? That's kind of tricky, isn't it? 'Cause I know what you're thinking, right? The capillaries, they have what? Fast or slow blood flow? Right. All right, let's stop at 120. Yeah, y'all just can't decide. Healthcare, women, and men. All right. It actually does decrease. Your intuition was correct. But why is that? How can we describe that in terms of the continuity equation? A1V1 equals A2V2. If this is my A1, why, if A2 gets so small, does V2 not just shoot out the roof like a finger over the water hose? Can I explain why that is? It just doesn't seem to make any sense. Does it make sense to you? You have more area. So the capillaries, you got a whole bunch of capillaries, but you only got one aorta coming into them. So the overall area, A2, is actually much bigger than the area A1 because it's not just the area of an individual capillary, it's the area of all the capillaries together. And so that's why I have a much bigger area here. So A2 isn't actually going down. So I misled you to think that. A2 is actually going up, and that's why V2 is decreasing. That's awesome, Dre. Okay? That's pretty cool, huh? Like, go tell your friends that. Like, first you got to tell them about flow rate and the continuity equation or the flow equation, and then, the circulatory system and the systemic circuit, and then pose this question to them and see what they say. All right. As blood flows through the aorta to the capillaries, the pressure differential drops. What happens to the flow rate? Um, we're going to skip this, okay? I'm sorry. Yeah, we'll skip it for now. All right, we might come back to it later, but let's skip it. Okay, let's look at intravenous medication. There's a whole section in your book on this. We're not going to spend much time on it. Uh, how do we administer medication via an IV? And they give some problems let's see, we'll just sort of work through this one where you have a bag of a certain volume, right? Your IV bag that sits up on the pole, and it empties through a needle of a certain size that you put into your arm, and it has a certain length, and we want to empty it every 30 minutes. How high must the bag be hung? Um, so first of all, our flow rate, Q, is delta V over delta T. And we know that we have 500 cubic centimeters, and we want to empty it in a certain amount of time. Like we want to empty it in 30 minutes. So we have 30 minutes times, we want to put this in SI units, or at least in seconds. So we say 60 seconds over 1 minute. And that's going to give us our flow rate, which turns out to be 0.278 cubic centimeters per second. Okay, that is our flow rate that's required in order to empty this IV bag in that amount of time. And so that is our Q value. Um, then we can calculate the pressure, because I know that Q in addition is equal to this our Poisson equation, pi r to the fourth delta P divided by 8 eta L. And so if I want to know then what must be the change in pressure, I would say solving this for delta P, I would have 8 eta LQ divided by pi r to the fourth. And we have all those values there. Now that we know our flow rate, we can figure out our change in pressure, which is going to be 4,400 pascals. Yeah, it should be pi r to the fourth. Listen, you're not going to have to do calculations like this, but I just want you to see that it is something that you can calculate, and that you know, people that design these sorts of things, these intravenous delivery systems, that they have to think about what are the radii of the tubes, the needles, the volumes of the bag, the height of the bag. But here we need a 4,400 pascals pressure. And then we want to know our height, and remember that our pressure is equal to rho GH. We saw that before, right? The pressure due to a height, we had several sources of pressure, and one of them is that you have this column of fluid that sits on top of the point, and so our pressure is equal to the density times the acceleration due to gravity times the height. And so we can use this to calculate at what height do you put the bag, which is equal to P over rho G. And it turns out, taking the density, say, of water, it's about 0.72 meters. And if you make that lower, if you lower it from 0.72 meters, then it's not going to empty in the same 30-minute period. Or if you make it higher, it'll empty at a faster rate. Now IVs, you know, they have pumps that actually regulate it more. But, you know, used to, they didn't have that. You just lifted it up or put it down, and it would change the rate at which it went into your body. Okie dokie. Again, you're not going to have to calculate anything like this, but I do want you to understand, you know, sort of qualitatively that we can do these things, but you're not actually going to have to calculate that. Okay? All right. What if it's a more viscous fluid? What's going to happen to H? Will H increase, decrease, or stay the same? Let's do this as a clicker question. Does it increase, decrease, or stay the same? I mean, this is based on basically putting water into your body, or a saline solution. But what if instead you want to put blood into your body in a transfusion? Then how would it change? Would you need to have it at a bigger height, A, a shorter height, B, or C, the same height? Does the viscosity matter at all? I want to remind you that viscosity is given by the Greek letter eta. A higher eta means a more viscous fluid. All right, y'all doing well. I'm going to stop at 105, 105, so just a few seconds left. Okay, good. A is right. You probably know that intuitively. Well, let's look at the math and see how that works out. Uh, if I make eta bigger, using blood instead of water, I make eta bigger, that means that this is going to increase. So if eta, the viscosity, increases, that means that this value is going to increase. And if that value increases, P, then that means that this value will increase. All right? So if our viscosity increases, it requires a bigger pressure. We know that intuitively, I think, that if I'm trying to push maple syrup through a hose, that's a lot harder than trying to push water through a hose because it's more viscous. And if I need a bigger pressure, then that means I have to increase the height of the bag. All right? Squeezing the bag increases the flow rate as well. You might have seen nurses come in and they squeeze the bag to make more go in. Maybe not, yeah. Anyway, squeezing the bag increases the flow rate. And this is an application of which of these? Is it Pascal's principle, Boyle's law, the ideal gas law, or Charles's law? Charles's law, well, never mind. Which is it? Is it, which of those? All right, let's stop at 45, 45. It is Pascal's principle. Very good. So, well, sort of good. Pascal's principle says that an external pressure is felt throughout the system. So if I think about my Poisson equation, if I increase the pressure right here, it increases the flow rate. And so if I apply an external pressure or a force to that bag, that pressure is felt all the way throughout the system. It's transferred by the incompressible fluid all the way down to the needle that sticks into your arm. Okay? All right. Let's see. So don't really fret the numbers on this. I'm really looking at relationships. Coronary arteries. Artery can be blocked with cholesterol. And like in the Poisson equation, we see that if we change the radius of the artery, that affects the blood flow. So if I have Q pi r to the fourth delta P over 8 eta L, that if I change the radius here, then that's going to affect the blood flow. But I still got the heart still working, and it's still putting that same pressure onto it. So uh, if I change this radius of the of if I change the radius of the artery, it actually causes the pressure to go up, the systemic pressure. We sort of talked about that already. Right? Y'all clear on what I mean by that? Everybody good? Yes? No? If I make my radius smaller, right, and my flow rate remains the same, then it increases my overall pressure, the blood pressure in your body. Let me write that in words, just make sure it's clear. If R goes up, or excuse me, if R goes down, it gets blocked, so the radius decreases, the pressure, delta P, increases. That's the systemic pressure. And we talked about, I was just doing that to confuse you, but the localized pressure actually decreases. Did that confuse you too much? Okay, the local pressure gets lower, but the overall pressure gets higher. All right, let's try these clicker questions. Try the one on the left. A decrease in the radius of the artery will require what change in pressure to maintain the same flow rate? All right, we'll stop at 32. 32. Okay, good. The answer is written right here, right? But you want me to still give y'all a joke, or is that too easy? Yeah. Well, it's not even really a joke. It's just sort of a funny story. It's a little vulgar, again, because I'm just sort of feeling that way today. But I had this idea at my house, because guys especially, like when you get up, you go to the bathroom. What do they call the bathroom? I don't like a guy's name. The John. You ever heard that? I'm going to the John. Ever heard that? I decided that I was going to call the bathroom the gym, like Jim instead of John. So that when I get up in the morning, I can say, hey, I'm going to the gym. And that just sounds a lot cooler. Don't you think? So we can all call our bathroom the gym instead of the John. Okay. Let's try this next one. A decrease by 10% of R causes a change in P of what? So if I decrease R by 10%, I know that my P is going to increase. How much is it going to increase? Is it going to increase by 10%, the same amount? By 8%, a little bit less amount? By 30%, a lot more? Or by just 1%, or just a small fraction of that? Think about the answers. You can figure out the answer without really knowing the numbers necessarily. Let's stop at 45. 45. All right, C is right. And you might say, gosh, how was I supposed to know that, right? But look at the equation. If I have a change in R, how much does it affect P? What if I change R by a factor of 2? By how much must P change? Not 2, right? By 2 times 2 times 2 times 2, which is a factor of 16. Okay, so the point is here that if I have a small change in R, it affects the pressure a lot because it's an R to the fourth. The flow rate is heavily dependent upon the radius, or in this case, the pressure is heavily dependent upon the radius because it's an R to the fourth relationship. Don't worry about the number so much. We're looking for the biggest number that there is. It's definitely not the same. It doesn't change by the same amount. It doesn't change by less or even by just 1. It's going to be by a factor of 30. So C is the right answer. Or rather, yeah, C. All right. Okay. Arterial collapse. We talked about this. Does somebody have their book? Because I don't think this is in your book. Can I, you mind if I look? She's got it right here. Just double check. It's very certain that it's not. Yeah, it's not in your book. So I'm going to sort of cross this out right here. We've already discussed it. It's not going to be on your test. So you can just get rid of arterial collapse. All right. Let's see. The lungs. The lungs bring oxygen to the blood from outside air. And Boyle's law, for Boyle's law, PV equals constant. We put it together with Charles's law to make the ideal gas law, the PV equals nRT. But right now we're just worried about Boyle's law. Describes how air comes into the lungs. The lungs expand, increasing V and decreasing P. Right. So if V goes up, that means that P has to go down because the product of those two, pressure and volume, have to be constant. And so the lungs don't actually expand, the chest cavity expands. And that, because by using my muscles to expand the chest cavity, that causes the volume to get bigger, the pressure to go down, and then that high pressure air rushes into the lungs. So that's an application of Boyle's law. And as I said, the lungs are not muscles. Instead, the muscles around the lungs contract or relax to open the cavity. All right, I have a video I want to show you. We'll come back to the iron. This is about the iron lung. Let me go ahead and show you that, and we'll